Okay, for low pass filter, this is a single pole active low pass filter. This is a quite simple one. This when you see this kind of configuration, it is actually a unity gain, so we don't have any resistors in the feedback of the amplifier, and we know that AV is equals to 1 for the unity gain, and this portion is actually the portion that determine the cutoff frequency of the filter. Okay, and this is the same filter, but this time around we put in the resistor R2 and R3. So with this resistor, now this low pass filter, single order low pass filter, will have gain, and the gain is determined by 1 plus R2 over R3. Okay, so as usual, when we try to analysis how we get this, is actually we take into consideration the voltage on each of the terminals, the non-inverting terminals and the inverting terminals. So now the source comes from Vin on the non-inverting terminals. So you know that at this terminal, the input impedance, input impedance is very high, so does not allow current to go into op amp. Okay, so there will be no current across this portion. So here I equals to 0 in ideal case. So here also I equals to 0. Okay, we call I plus I minus here. So since the current will not flow into the op amp, so the current will actually go to the ground here. Okay, so in this case we can find the V plus using voltage divider rule. So if you redraw this, you can put in something like this. So this is V input, and then this is R1, and then this is the capacitor, this is the ground, and this portion is actually V plus, this one is R1, this one is C1, and you can find the value of V plus by taking this voltage divider rule. You have XC1 over XC1 plus R1 multiplied by Vn. Okay, and then you can solve for this. You will get these terms. You will get 1 over 1 plus S R1 C1. Okay, you will get this term V plus. Okay, isn't it? Vn. Okay, and then for R2 and RT, you know that V plus equals to V minus. V plus equals to V minus, and the same analysis can be made using this V out. You can draw R2 and then R3 goes to the ground, so this is V minus, this is R2, this is R3, and you can find V minus by taking the voltage divider rule. V minus equals to R3 over R2 plus R3 V out. Okay, and then this is the gain, actually V out over V in. So you can take this V plus equal to V minus, and you can finally find the gain V out over V in of this low pass filter, first order low pass filter. Okay, and you can also find the magnitude because we have the term S in this. Term S in this equation, and then you can just convert S equals to J omega, and you can find the magnitude of this component, and then this is the magnitude. Okay, 1 over square root of 1 plus omega 1 R1 C1. This is actually C1. Okay, and what you can see now here, this term is actually determine the cutoff, ataupun kita kata omega C lah. So omega C, the cutoff frequency. This term determine the cutoff frequency of this low pass filter. So by definition, we can find the tau. Tau equals to 1 over RC, and tau equals 1 over RC, and it is a time constant. So the cutoff frequency, when you put into consideration, you know that the cutoff frequency is actually negative 3 decibels. Negative 3 decibels below the passband here. And how you get actually 3 decibels? This is actually comes from this term. Okay, so the maximum. So when we find the cutoff frequency, actually we put into the time constant into the omega. So what we have is actually 1 plus omega is R1 C1 multiplied by R1 C1. What we can get is 1 over square root of 2, which equals to 0.707y. And then when you put put it into a log term, so you can multiply by 20 log 0.7071. What you get is actually negative 3 decibels. So this is actually the negative 3 decibels that corresponds to the cutoff frequency on the plot. Gain versus frequency plot here. Any questions so far? Okay.
No question, Doctor.
Okay. So just remember, this single order low pass filter can be cascaded into higher order low pass filter. For example, we can cascade 4 times in this case. So this is unity. All 4 low pass filter here is a unity low pass filter. So the output becomes fourth order low pass filter. So this is the first stage, and then the output connected to the input of another non-emitting low pass filter, and the output of this is connected to another low pass filter. So this is the first stage, this is the second stage, this is third stage, and then this is the fourth stage of the low pass filter. And you know that I have mentioned in the video, the order of the filter will make the transition band from the pass band to the stop band much steeper. The roll off rate will be reduced from negative 20 decibel per decade to negative 40 decibel per decade for the second order low pass filter, and then further reduced to 60 decibel per decade and negative 80 decibel per decade for the third order and the fourth order low pass filter. Okay. All right. Next, this is another low pass filter, but this time around it is inverting low pass filter. Okay, so the input is supplied to the input voltage is supplied to the inverting terminals, and the non-inverting terminal is connected to the ground. Okay, you can use similar analysis to find this equation of gain. So here we know that V plus is equals to 0 because it is connected to the ground, and at this point V minus equals to 0. We call it as the virtual ground, virtual ground here. You know that because for this analysis of amplifier, we know that both inputs sticks together, so we can say V plus equals to V minus. Thus, at this point, V minus also negative. V minus also equals to 0. Okay, so since there is no current that passing through the op amp, the current will not go into the op amp and go upwards. Okay, so we can say that the current here, let's say this is I1, this is I2, okay, this is I3. So this one becomes, actually this is become I1 again. Okay, because the current go here, split into I2 and I3, split, and then it's combined again into I1. Okay, so we can say that Vin minus 0 over R1 equals to 0 minus V out over, this is a parallel between C1 and R2. Okay, so you can solve for this and you will get this term. Okay, so I skip the derivation. I think I already have supplied the derivation in the previous lecture notes for this non-inverting amplifier, inverting amplifier, as well as differential amplifier. Okay, you just can take a look back at the videos. Okay, now we have high pass filter. Okay, for the high pass filter, the difference between the high pass filter and low pass filter configuration, you can see that for high pass filter, the capacitor comes first. For the low pass filter, the capacitor comes later, downwards here. Okay, this is the capacitor here. Okay, that is connected to the ground. And for high pass filter, the resistor that is connected to the ground and capacitor comes first, right after V input. Okay, so you can use similar analysis, okay, by taking into consideration this voltage here, using voltage divider for V plus, and then V plus equals to V minus. You can get at this location, so this is a V minus, and then again you can use the voltage divider rule for this portion. Okay, this portion also voltage divider rule, this one also voltage divider rule, and you can get these terms. Okay, again this C1 R1 will determine the cutoff frequency of the high pass filter. Okay. Okay, now filters are second order. So the nth order of the filter is directly affected by n poles in the filter design. The number of poles is indicated by the number of RC elements present in the circuit. Fundamentally, an increase in the number of poles will increase the roll of rate by 20 decibel per decade per pole. Okay, so if you have, like I mentioned before, 2 poles means negative 40 decibels, 3 poles 60 decibels, 4 poles is 80 decibels. Okay, thus a second order filter will have a negative decibel per decade roll of rate, which is much steeper than the roll of rate of the first order. Okay, and I think I have mentioned in the previous video that the most designs of these second order filters are generally named after the inventor, where we have a common filter such as Butterworth, Chebyshev, Bessel's, Salenky, for example. And all this type of filter is actually available in the low pass filter, high pass filter, and band pass filter, as well as a band stop notch filter configurations. Okay, so actually this Salenky is one of the most widely known and popular second order filter design, because it's only require one single op amp to have gain control of the second order filter. Second order filter which has a steeper transition between the pass band to the stop band. Okay, so this is a generalized unity gain Salenky topology. So we have, you just remember this kind of configuration. So we have Vin that is connected to Z1, and then it has a feedback to the op amp, and then afterwards we have Z2 and Z4 that is connected to ground. And this is as usual the configuration for unity gain. Okay, so the difference between the high pass filter and low pass filter configuration for this Salenky is just the location of the capacitor and resistor. Okay, so for this generalized topology of a Salenky filter, you can have the transfer function of V out over V in of the system is given by this Z3 Z4 over Z1 Z2 plus Z1 Z3 plus Z2 Z3 plus Z3 and Z4. Okay, so it is sometimes we can use different value of resistor and capacitor in this Salenky topology, and when we do that, we can calculate for the cutoff frequency that is given by 1 over 2 pi R1 square root of R1, R2, C1 and C2. Okay, where does 2 pi comes? It's actually it comes from this omega, and 2 pi f. Omega equals to 2 pi f. So if either you can use omega c or fc, it depends, but you have to compensate for f for 2 pi if you use the frequency fc. Okay. So if resistor and capacitor values are the same, means R1 equals to R2 and C1 equals to C2, we can simplify the cutoff frequency of the filter by just taking this Fc equals to 1 over 2 pi Rc, or you can have omega c equals to 1 over Rc. Okay. Alright, so this is a low pass filter unity gain for the silent key. So as usual, when we said about low pass filter, so what comes first after the voltage in is actually resistor. Okay, so we have resistor, and then in feedback we have capacitor, and the capacitor that is connected to the ground. So this is, you can just memorize one either low pass filter or high pass filter, and remember one just low pass filter, and you can get the high pass filter configuration as well. It's just a compensation from low pass filter for the high pass filter. Okay, so you just replace the value of R1 Z into the R and C into the term TS. So what you get is, you get this is for the transfer function for low pass filter silent key with unity gain. Okay. If you have some time that you can spend, you can just prove the expression of AV for the low pass filter to have this. Okay, so this is you can get the magnitude of this TS term, and you can get the gain for the unity silent key filter as something like this. Okay, and the omega C will be attenuated at -6 decibels per decade. So you have this kind of so this is the frequency, and then this is the gain here, and this is actually -6 decibel per decade. And -6 decibels. And the cutoff frequency is located at -6 decibels because it's actually and the slope is negative dB per decade, because this is a second order system which has two capacitors. So two capacitors means we have two poles. When we have two poles means we have -20 decibel multiplied by 2, we have -40 decibels. Okay? And the roll-off rate is -40 decibel per decade. Okay, so this is a normalized low pass frequency response. Okay, okay, this is a first order, and then this is a second order. Any questions so far? Okay, and you also remember that we have mentioned earlier, when we said about second order system, it will also have the component of damping factor as well as the quality factor. Zeta damping factor is Q is quality factor. So both will affect the response of this filter. Okay, so if we have low value of zeta, which means you have high value of quality factor, what you get is you get a response that have you have a peak. You have a peak on the cutoff frequency region. Okay, so the higher the value of Q, or the lower the value of zeta, the higher the peak will be. Okay, so in this case, you can see that zeta equals to 0.7071, you can get a very smooth plot here. Okay, that is same as our cutoff frequency at -3 decibel per decade. Okay, then if you have a value zeta that is higher than 1, so the system will have a response that we call as overdamp. Okay, it will not have oscillation, it will not have any peak on this cutoff frequency region. Okay, and the response or the design of this value of Q or zeta is depends on the what are the things that can or you want to design. Okay, next. Okay, so I have explained in the previous video about this quality factor and damping ratio. You just take a look at that at the video, and I have also provide okay, I forgot to put in the link. I think I put it on the PowerPoint, but it does not appear on the PDF. So just take a look back later on. Okay, and I also included some examples that you can see. You just follow these websites and many other websites that actually you can see the examples for a second order filter. Okay, and now we have high pass filter, again using the silent key topology. Now what we have is actually we have the capacitor that is connected to the V input, and then we have resistor that is connected to the ground. So again, this is a unity gain filter, second order filter. So assuming R1 equals to R2 and C1 equals to C2, we can get this transfer function of this high pass filter. And then you can get this expression by taking the magnitude of this. You can get the term here. Okay, so that's it for high pass filter. Again, when you have a second order high pass filter, you will have 40 decibel per decade. This is not actually negative. It should be positive. It should be positive. And the slope should be positive because it's inclining, not declining position. Okay, any question? Okay, I assume no questions. Now we introduce the resistor R3 and R4 in the generalized silent key topology. Now we have our gain here. Okay, so the gain here is given by, so now the term becomes like this, and actually what you have is you have the gain component. Okay, the gain component here is actually R3 over R4, something like 1 plus over 3 R4 over R3, R3 over R4. Okay, it looks just something like this normal filter for the R2 over R3. So itulah over R3. So we have here R4 over R3 okay, R4 over R3 kat sini like this. Okay, so maybe I will do a separate video for the derivation for the silent key later on, and how you can get this term. Okay, so for the time being, just accept that this transfer function for this low pass filter will have this term. So I think this K term here is actually the gain here 1 plus R4 over R3. Kita tak mention dalam ni. K. Actually, K is the gain. K is the gain for 1 plus R4 over R3. Okay. This is for the low pass filter again. For this one, okay, this is a simplified version from the previous one. Okay, now what we have for this high pass filter, and this is a simplified version of this transfer function for the high pass filter, silent key. And we have here this, like I mentioned before, we can cascade. The filter to have a higher order filter. Let's say we want to have a 5th order filter, 6th order filter. Okay, so what you can do is you just cascade the 1st order and 2nd order filter. So if you have a 1st order, of course you only have 1st order filter, and 2nd order filter, of course you have a 2nd order filter. But if you want the 3rd order filter, so you can either cascade 1st order filter 3 times, or you can put in a 1st order filter cascade with 2nd order filter. Okay, again, if you want to have a 4th order filter, yes, either you cascade 4 1st order filter, or you can cascade 2nd order filter 2 times. Okay, so it just depends on what are the things that you want. Okay, all right. Here example of how many order of this filter, high pass filter. Anyone? 3. 3rd order. Who agree this is a 3rd order filter, or any other opinion? Someone? Cakap le, tak payahlah tarik. Susahlah nak tengok dekat sana sini.
6 order, Doktor.
6 order? Pasal apa 6 order?
Sebab yang tu ada general bus.
Apa dia?
Tu order. Setiap tu dia ada second order. So ada 3 kali. So ada 6 order.
6 order. Okay, it is actually 6 order filter. Okay, does it have unity gain, or it does have some gain? Is it unity or have some gain? Someone? Anyone? Ada?
Ada gain.
Okay, so actually this configuration have some gain. Which is, you can see that from this portion is actually have R1 and R2 here. Okay, the same lah. Okay. Actually this point, this output is connected to R1, so you can redraw something like this. So this output is connected to R1, so let's say we have connected to R1, so this is R1, and R1 is connected to R2, R1 is connected to R2, and R2 connected to the ground. So similar to this diagram. Yeah. It's just they put it this way, but it's actually the same one. Okay, so this is a 6th order filter with silent key topology. Okay, so it depends. It depends on this R1. Sorry, the resistor and capacitor will determine the cutoff frequency for this high pass filter. Okay, so this is a 2nd order and higher order amplitude response. Usually we will do the analysis for 2nd order system. Remember, in the control system we only do for the 2nd order system, and for the rest 3rd order and higher we can sometimes approximate the response to the 2nd order system. Okay, so for this response is actually it depends on these values of zeta. Again, when we have low value of beta, we will have a high oscillation, and if we have low value of zeta, we do not have oscillation in case of zeta equals to 1 and greater. But if we have zeta that is close to 1, so the oscillations become less and less. Okay, let's say 0.8, 0.7, 0.6, and so on and so forth. Okay, and now we have band pass filter. Okay, for the band pass filter, this the simplest configuration for the band pass filter is we can simply cascade between the high pass filter and low pass filter in series. So this will generate a wide band filter. Okay. For example, if we cascade first order high pass filter and first order low pass filter, we will have a 2nd order band pass filter. And if we cascade 2nd order high pass filter and 2nd order low pass filter, we will have a 4th order band pass filter. Okay. Narrow band filter of higher order consists of cascaded as 2nd order silent key band pass filter. So if we cascade something like a high pass filter, we get the wide band filter. Wide band filter means that the bandwidth of the band pass is greater, is higher. Okay. So this is this diagram that illustrate that how to connect these high pass filter and band pass filter to get a band stop filter. Okay. Okay. This is actually when we have without the capacitor here, we only have is a high pass filter, right? So only high pass filter. But when we put in the capacitor parallel to R3, so what we have is actually we have this band pass filter. Okay, this is non-inverting configuration. So if we have this kind of configuration, so without this is actually a band pass filter. Without this is a band pass filter. So when we include the capacitor here, it becomes band pass filter, but in this case is inverting configuration. Okay. Alright, so next is this is the band pass filter in silent key configuration. So you can see the difference between this high pass filter and low pass filter configuration. Now what we have is we have this kind of configuration, we connect the only the capacitor to the ground, and then we have another portion here. At this portion we have a resistor that is connected to the ground. Okay, all right. Any questions? So previously in the low pass and high pass filter, there is no component here. Only what we have is only this component. Okay, but for the band pass filter, we add capacitor right after the resistor. Okay, so again, for this one, this is the transfer function for this band pass filter here. So you just can put in the value for this K is actually this term 1 plus R2 over R1. Okay, right. So for this, for band pass filter, you can find the center frequency. Center frequency for the band pass filter is 1 over 2 pi RC. So in this case, actually we have same R, same C, same R and same C. Okay, you can find the cutoff or center frequency at 1 over 2 pi RC, and the gain is given by this G equals 1 plus R2 over R1. So G is actually, in this case, we have K. So K, so the gain 1 plus R2 over R1. And we can relate between these in not. So this is the gain and quality factor. So here, this is actually depends on this this portion over here. There's a term 3 here. Okay, the term 3 here, so it can relate to this portion where we cannot have the gain more than 3. We cannot have the gain more than 3. If we have the gain more than 3, then it becomes it can lead to the instability of the system. Let's say we have 3 plus 3 equals to 0, right? 0 plus something equals to 0. So there is no portion of this. Okay, so if we have greater value than 3, let's say we have 5 equals to negative 2. So we have negative 2 over RC. So we have this S square minus 2 over RC S plus this term 1 over RC square. So it can either be stable or unstable. Like we have learned in the control system, where we can find the stability using the Routh-Hawes criterion. Okay, so the silent key, usually when we design the system using the silent key filter, regardless of high pass filter, low pass filter or band pass filter, usually we use low value of Q. We use low value of Q, quality factor. So meaning that there is not much peak on the response, something like this. So not so high the peak value of this plot. Okay, but if you want to have a high value of Q using the second order filter, using a single op amp, you can use a multiple feedback multiple feedback topology. That one can use a queue that is higher than the silent key configuration, but it is just out of scope of this our discussion. Okay, but you can just take a look back on the notes from your analog filter, or you can just Google around about the multiple feedback topology, or you can just go to this. I have provided the link actually here, where you can learn more about this filter. Okay, so you can just go to this. You just can Google active filter design techniques, SLOA 88, and you can find a very good explanation about the filters. Okay, now I think we comes near to end of our discussion. Here we already finished this one. Okay, this one is related to this narrowness of the bandpass filter. So if we have a low value of Q, so you can see that the peak for this bandpass filter, I think this one is I'm not sure it's using other types of configuration. I think it's not the silent key. I think this may be just comparison in using the multiple feedback topology here. So we have a low value of Q compared with a high value of Q. Here we have 10, Q equal to 10. So you can see that the narrowness of the band pass band of the band pass filter. Okay, so yeah, it depends on Q lah. This is example of so I found from this a paper from 1998 written by Song et al. So they have this kind of instrumentation amplifier, but they embedded a high pass filter onto the instrumentation amplifier, where it includes the capacitor here. It includes the capacitor here. So this is called as a quasi high pass filter. Okay. Next, this is the last topic for the filter. So we have a band stop filter. Okay, band stop filter. You have heard about a twin T band stop filter, right? So usually you can see the twin T band stop filter using a passive component without the inclusion of the amplifier. But we can also modify the twin T band stop filter. This is the original twin T band stop filter. So you can make it active twin T band stop filter by including by the inclusion of this portion. So this is actually amplifier with a feedback 1 plus R2 over R1. Okay, so this is just a band stop filter with some slight modification. Okay, so for this kind of band stop filter, this is the mid frequency or the center frequency, 1 over 2 pi RC. Again, it's about the same lah. If you use the similar value for C, C, R, 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 C, same value, then you can easily determine the value of mid-range, mid frequency or center frequency. Okay, and this is the gain. Okay, 1 plus R2 over R1 is given by this portion. And then we have the passband gain. The passband gain A not equals to G. Okay. And then the rejection quality is given by Q equals to 1 over 2 2 minus G. So actually this quality factor comes from this portion. Okay. Okay. Similar in the previous examples where we have our gain for passband that is related to these terms, right? 3 minus k. Okay, any questions? So this is just some writing. So the 20 circuit has the advantage that the quality factor Q can be varied with the inner gain G without modifying the mid frequency. So we have this, the mid frequency is determined by the components of this 20 configuration here, and we can just simply change the gain by varying the value of R1 and R2 here, right? without the need for change the value for these R and C values. Okay. However, Q and A M cannot be adjusted independently because of the, you can see the Q AM is what, the mid pass band apa AM. Nanti saya tengok what is the AM. Okay, to set the mid frequency of the passband, FM and C can be specified and solved for R. And because the dependency of Q and AM, there are two options to solve for R2, such as to set the gain at mid frequency or to design for a specific Q. So either this one or this one. Okay. Okay, next one. This is the last slide for this chapter. So this is the band stop filter response dependent on the value of Q. So you can see here, if you have high value of Q, so the band is very narrow. The band is very narrow. Maybe maybe you can filter out a single frequency. Okay. But you have a lower value of Q, so you can see the difference here. It has a slightly wider band as compared to the high value of Q. Okay, so if you want to, let's say, just filter out 50 Hz frequency, power line frequency, so you can just use the pass band, stop band filter with a high value of Q, so that you can then determine the cutoff frequency. So you can determine the cutoff frequency by just using this formula, and then you can determine value of R and C. So by this you can just easily can design what are the frequency that you want to exclude in your signal processing signal conditioning circuit. Okay, that's it for